Okay, so welcome to Math 349, Operations of Order. This is lecture 37, so we're at the home stretch right now. So you should have really good progress at this point on both your chapter and your outreach article. This is not something that you can put off to the last minute. So you should really try to get drafts of those to me as soon as possible, as well as to the TA, so we can start iterating and commenting on that. If there are topics people would like me to cover on Friday or even today, just let me know. Is there anything in particular people would want to hear today? Okay. Was there? No? Okay. So what I'm going to do is I'm going to talk about Vandermonde matrices. I believe they made an appearance in colloquia this week. They did, yes. These are some of the more interesting types of matrices, and just trying to analyze them is a great way to talk about how to explain mathematics, how to write things up, how to go through a thought process. One of the greatest dangers in life is being misled by small examples. That things that are true in special cases do not always generalize. And so you always have to be careful. This doesn't mean you should avoid gathering data. I am a strong proponent of do special cases, build intuition, get your hands dirty. But just be careful when you're doing this. So linear algebra is a prerequisite, I believe, for this class. I'm going to assume everybody is comfortable with finding determinants. You just go to something like Mathematica and input the matrix and say, if you actually had to calculate a determinant, if the matrix isn't too big, you can do it without too much trouble. So for example, the determinant of, let's do the matrix that's just the 1 by 1 matrix, that's 1. Its determinant is, which is what? Just 1. All right. So now let's do a 2 by 2 matrix. 1, 2, 3, 4. Its determinant, and we'll denote that with the absolute value lines. And what would that determinant be? -2. Interesting pattern. 1, -2. What number do you think comes next? 3. And what matrix do you think would have determinant 3? 3 by 3, and what do you think it would be? Yep. What would be the next one? 4, 5, 6, 7, 8, 9. And so its determinant. And how am I getting these numbers? I'm just taking the numbers, from 1 to n squared, because it's an n by n matrix. It has n squared elements. So does everyone agree that its determinant is 3? Why not? So I can actually prove that its determinant is not 3. Its determinant is actually 0. I can do that math in my head. They don't let just anybody be a professor at Williams. You have to accept the job. Could you check to see if that's right? Yeah. Do you remember the way to check by writing down the first 2 columns? This only works for 3 by 3 matrices. If I give you 1, 2, 3, 4, 5, 6, 7, 8, 9, a quick way to calculate the determinant is 1, 4, 7, 2, 5, 6. And then when you go through, you do these 3 with a plus sign. And then these 3 with a minus sign. Do people remember seeing that trick to do 3 by 3 determinants? You can also do expansion by minors. And when you do all that calculation, you get 0. I'm not going to do that algebra. I'm going to just leave that to you to do. All right, so now the sequence is 1, -2, 0. Any thoughts about what comes next? I'm sorry? Why 1? Nobody starts over? What could you do to try to get a good sense of what comes next? Yeah, do the 4 by 4. All right. 1, 2, 3. Do you want to do the 4 by 4, or do you want to do a larger matrix? I'm sorry? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And unfortunately, we can no longer use the trick. So we have to expand by minus. So this would be 1, and then the determinant of 6, 7, 8, 10, 11, 12, 14, 15, 16, right? Minus 2, and then it would be 5, 9, 13, 7, 11, 15, 8, 12, 16. Right, is everybody comfortable with expanding by minus like this? Okay, are you able to do this in your heads? Wow, I mean, when I was in school, they just really drilled this into us to be able to do stuff like this in our heads. Okay, I get 0. What do you think? So now the sequence is 1, -2, 0, 0. What do you think comes next? 0. If you want, I'll do another one for you. Give me what size matrix you want. It's 0. I'm really fast. Now, I also talked with Paul before class, and I planted with him asking the 8 by 8, so I had that ready. So does somebody else want to give a different one? There's obviously something going on if I know it's 0 this quickly, right? Let's look at what's going on. We have the matrix that's 1. Then we have the 1, 2, 3, 4. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And the sequence is 1, -2, 0, 0, 0, 0, 0, going on and on and on. So whatever is happening, it takes a while for it to happen. When the matrix is small, I don't have enough freedom to see this interesting phenomenon. So can someone tell me, what does it mean for a matrix to have determinant 0? So as soon as you know the determinant is 0, you know something. What do you know? It's what? No, it's not invertible. So you could say it's vertible. I don't know if anybody has ever used the phrase vertible, but it seems strange to talk about something being invertible if you don't talk about anything being vertible. So it doesn't have an inverse. Okay, what does it mean if it doesn't have an inverse? What are the consequences are there about having a determinant of 0? I'm sorry? No, you've got it all off. The rows don't span and the columns don't span. So if you, it's not a basis. So the way to look at it is the determinant measures the volume of the parallel pipette spanned by the rows or the columns. And so if the determinant is 0, it means, in 3 dimensions, we actually have a plane and not a parallel pipette. So it means that one of the columns can be written as a combination of the others, or one of the rows can be written as a combination of the others. Can anybody see any relations between the rows? Well, if they're linearly independent, then that would mean the determinant is non-zero. So in the first case of the 1, linearly independent. In the 1, 2, 3, 4, they're linearly independent. So in the 1, 2, 3, 4, 5, 6, 7, 8, 9, there has to be a dependence. Excellent. So 2 times second equals first plus third. Linearly dependent. And that will extend to the n by n matrix as long as n is at least 3. Why does this break down when we try to look at the 1 by 1 and the 2 by 2? Right, we don't have a third row, right? We have, as a result, the second row doubled is always the first plus the third. Well, if I don't have a third row, I'm not going to have a linear dependency. And in the first case, I don't even have a second row. So this is something that will only kick in eventually. It does kick in, and once it kicks in, as an exercise, you should now prove that if I give you any n by n matrix, and this is not going to be a terrible proof, because you're going to have 1, 2, 3, dot, 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 n. The next row is going to be n plus 1, n plus 2, n plus 3, dot, 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 2n, and then 2n plus 1, 2n plus 2, 2n plus 3, dot, 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 2n, I'm sorry, 3n, and just going all the way down to n minus 1n plus 1, dot, 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 n squared. And so now you should hopefully be able to show without too much trouble that twice the second row is the first plus the third. So whenever you are teaching, it's always nice to have examples. So if you're teaching linear algebra, it's nice to have some examples of matrices you can look at. And so if I'm giving a 2 by 2 matrix, 1, 2, 3, 4, that's not a bad matrix to write down. But if I write down 1, 2, 3, 4, 5, 6, 7, 8, 9, that's actually going to be a matrix with determinant 0. And if I look at larger and larger matrices like this, they're all going to be degenerate. They'll all be non-invertible matrices. This is one of the dangers of working with just integers. So if I put in any random real numbers, it's unlikely I would have something like that. All right, so what I want to do now is I want to talk about Vandermonde matrices. And so they come up in many things, absolutely beautiful. There's a couple of ways of writing them. I'll write it this way: 1, 1, 1, dot, 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 1. Did you do it this way in your talk with ones in the first? Okay. And then it'll be x1 squared, x1 cubed, dot, 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 x1, you do to the n minus 1?
Yes.
Okay. And then I'll go all the way up to x to the n minus, x sub n minus 1, and then go all the way down to x n minus 1 to the n minus 1 power. And so what's the size of this matrix? N by n. And the determinant, it's unclear what the determinant is. That's what we want to figure out. So this matrix, or matrices like this, occur in a variety of problems, from trying to do fast multiplication to trying to understand eigenvalues that model physical phenomena. And it's extremely important to calculate the determinant. And here, x1 through xn minus 1 are just free parameters. Okay? So how could we start to build intuition about this? Yeah, we could do it for small n. Let's build intuition. So when n equals 1, determinant equals 1. When n equals 2, it's 1, x1, 1. Is this right? We were supposed to go up to n minus 1, right? Does it start off as x1 or does it start off as x1 to the 0?
I did mine with ones across the top column.
And then he goes up to the nth power? Not the n minus first power. Or did you have x1 here, or do you have?
I have ones across the top row.
As well, okay.
Yeah.
Okay. So what you would have is you would have x1 to the 0. Yes, and then this would be to the first power, to the second power, to the n minus 1 power. There you go. And so when we do that, then we would have x1 to the 0, x1 to the 1. So this would be 1, 1, 1, x1. And we would just get x1 minus 1. Just double check and make sure that this is the correct definition. There's a couple different ways one can write things. All right, so okay, so this is a slightly different definition. All right, so the definition online is a little bit different. So you had all ones in the first row and all ones down the first column. Because that's not normally the one I use, and I just looked online, and this is the one that I normally use. And so you might be doing a very special case. So let's rewind things a little bit, and I'm going to change the definition a little bit just so it matches. So let's do it this way. And again, it sometimes takes a while to figure out what's the right quantity size. Let's do x0, x1, x2, all the way up to all right, so we want to do it. So this would be n minus 1. And this would be x0 to the n minus 1, x1 to the n minus 1, xn minus 1 to the n minus 1. And so the real issue is, I think, do you want to start your counting at 1 or do you want to start your counting at 0? And do you want to set x0 to equal 1 or not? So start counting at index 1 or 0, set x0 equal to 1 or not. So these are some decisions you can make. And depending on, if you make some of these decisions, we've talked a little bit about how you can sometimes adjust your quantities by rescaling without too much of a deal. Whether or not I want to start counting at 0 or 1 is not a big deal, but is there some loss in generality in assuming that x naught is equal to 1? And you said that you were looking at it with ones down the first column and the first row. Okay, so that's a very special Vandermonde matrix. And the more general one is I just have some extra parameter x naught, which may or may not equal 1. Okay. So now I would have, what I like about this notion is now if I have an n by n matrix, I have n parameters. X naught, x1, dot, 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 xn minus 1. And so the question is just, do you find this annoying that we're counting from 0 to n minus 1? Would you rather count from 0 to n minus 1 or from 1 to n? Doesn't really make too much of a difference. You just have to be careful and just watch what you're looking at. So if we do that, now when we go to the 2 by 2 matrix, it would now be the following. It would be x0, x1. So it would just become x1 minus x0. Is this enough for you to make a prediction about what's going to happen? All right, so let's look at n equals 3. So we'd have 1, 1, 1, x0, x1, x2, x0 squared, x1 squared, x2 squared. How do you want to expand this? I would probably expand around the ones. And so if we expand by ones, it would be 1, and then it would be x1, x1 squared, x2, x2 squared, minus 1, and then x naught squared, x2, x2 squared, plus 1, and then it would be x naught squared, x1 squared. And so if we expand things out, we would get x1, x2 squared minus x1 squared, x2 minus x naught, x2 squared minus x naught squared, x2 plus x naught x1 squared minus x naught squared x1. Does that look like anything nice to you? Now shift over. Mathematica.
Did you find what each x to be?
Well, they can just be anything. So by choosing different values of the x's, you would get different matrices. So the determinant is a function of the x's. You give me the values of the x's, and I get a determinant.
I think the top three, by the top column was all ones. Or the top row was all ones. Because x naught was one.
Right, but you said you had the top column and the top row.
Bro, yeah, all x sub 0 was one.
Well, I mean, what you can do is you can view the ones as just everything to the 0th power. So I can view everything that's going on over here. Oops. You know, I can view all of these is that's just x naught to the 0th power. And this is x1 to the 0th power, all the way down to this is xn minus 1 to the 0th power.
Yeah, I'm saying top row for me, x naught was equal to one.
Right.
So all those powers.
Right. And so you just had a very special case.
Yeah.
But you can view this, the reason we have all the ones for the first column is you can just view that as all the 0th powers. And so you give me different choices of the x's and I will get different quantities. All right, so now let me start the share. Let's see if I can share the screen here. Okay, so let's do in Mathematica, see if I can make this a little bit larger. So let's make M the following matrix. We had 1 x naught, and then and then it was x naught squared. So maybe this is a bit too large for the size. And then the next row would have been 1 x1 squared. And then the last one was 1 x2 squared. So there's our matrix. Our matrix form just allows me to write the matrix in a nice way. And then we want to find the determinant. So we just calculate determinant of M. And there's our answer. And now what we can do is we can do simplify determinant of M and see, can Mathematica simplify that? And it does. So that's interesting. It simplifies it as negative x naught minus x1, x naught minus x2, x1 minus x2. So what's interesting about this is this polynomial factors in terms of pairwise differences. I have x1, x2, I have x naught x2, I have x naught x1. I do have this minus sign outside. And if you look at it, the way we've written it, it's always the lower index minus the larger index. If we did it the larger index minus the lower index, how many signs would we have to change?
One.
Why 1?
Not necessarily.
Well, I think we would have to change all of the indices. You know, each quantity is the difference between two x's, right? the first x has the lower index, the second x has the larger. It's x0 minus x1. It's x0 minus x2. It's x1 minus x2. So if we switched it so that we always had the large index, to get from x1 minus x2 to x2 minus x1, that costs us a minus sign. So how many factors do we have? So we have a product. How many terms do we have in the product? 3. So how many minus signs will it cost us to switch the order? 3. And so I can actually get rid of this minus sign if instead I write it as x2 minus x1 times x2 minus x0 times x1 minus x0. So let me take over the screen share. So what we just showed here, in this case, is this equals x2 minus x1, x2 minus x0, x1 minus x0. This was not clear by looking at the algebra from just calculating the 3x3 determinant. This is the advantage of having something like Mathematica, where it can do a calculation like this. What do you think we should do next? 4x4. Do you want to do expansion by minus of 4x4 matrices? Yeah, but if you had to, you could. But then the problem is, at the end of the day, you're going to get a massive polynomial. And then the question is the polynomial going to be reducible? Well, let's think a little bit. If this is equal to this product, then that means the matrix has to be divisible by x2 minus x1. The determinant has to be divisible by x2 minus x1. So when I look at this, can you look at this and tell me if x2 minus x1 divides this? So how many of you remember your polynomial long division of polynomials with several variables? Well, what does it mean if a polynomial is divisible by x2 minus x1? So remember, x2 and x1 are completely free parameters. What would it mean if I tell you that you are a multiple of x2 minus x1? So what must be true if you're a multiple of x2 minus x1? So you can write it as some polynomial times x2 minus x1. But I claim that if there's a special choice of x1 in terms of x2, where you know what the value will be. I'm sorry? No, what were you going to say? So let's say you're a multiple of x2 minus x1. I claim that there's a really good choice of x1 as a function of x2, where you will know what the determinant is. Yeah, if x1 equals x2, what does the determinant have to equal? So when you look at this, can you look at this and tell me that if x1 equals x2, that it's 0? Well, let's see. If x1 equals x2, what's true about the first term? We get x2 cubed minus x2 cubed, that's 0. If x1 equals x2, oh, look, these two terms over here, the last two terms, they're the same, and one of them has a plus sign and one of them has a minus sign. I'm sorry?
Isn't one x not x2 minus x not x2?
Wait, but if x1 equals x2.
Oh, I got you. Yeah, that makes sense. My bad.
No problem. So here. Let's see if I can copy it. So if x1 equals x2, the first term is 0, second and third cancel. So we know that this polynomial has to be a multiple of x2 minus x1. So this polynomial is a multiple of x2 minus x1. Yes.
How do we know it's a multiple if we just try it when we have it?
Well, because we know that this is a polynomial. And we know now that if x2 equals x1, we get 0. So this has to be a multiple of x2 minus x1. Because no matter what x1 I take, if I take x2 to be x1, it's got to be 0. So that means this has to be a multiple of x2 minus x1. What else do you think it has to be a multiple of? So let's try that. So if you want to do, wait, what do you think it is?
Or maybe x1 minus x naught.
Okay, so if x naught equals x1, so now if x1 and x naught are the same, then the last factor is just going to be 0, right? And then the first and the second, since x1 equals x naught, cancel. Then first and second cancel. Third is 0. So this polynomial is a multiple of x1 minus x naught. And then the last one is if x naught equals x2. So if x naught equals x2, now let's see, the second term is now going to be 0, right? Then second term vanishes. And now x naught equals x2. So if you now look, the first term starts off with x1, x2 squared, and the second term ends with a negative x2 squared x1 because x naught is x2. So now the first and the third cancel. So this polynomial is a multiple of x2 minus x naught. So we get that this has to be some function of x naught, x1, x2 times x2 minus x1, x1 minus x naught, x2 minus x naught. So does everyone agree that we have to have something like this? Now, if we can trust Mathematica, it tells us that that function f has to just be the constant function. The goal is to, it only copied half of it. So this is going to equal some function of x1, sorry, x0, x1, x2, and I'm going to write it as a product 0 less than equal to I, strictly less than j, less than or equal to 2, xj minus xi. This is a fancy way of writing what we had. I'm taking the product of all pairs of the x's, and I'm writing it so that the large index comes first. So the small index can go from 0 to 1 less than the large index, and the large index can go all the way up to 2. Now, what is the degree of this polynomial? So what's the degree of the polynomial?
Or when they equal each other?
Well, the 2 degrees have to be the same, yes. So what's the degree on the right-hand side? So what's the degree on the right-hand side? This is a polynomial. What's its degree? Why is its degree 2? Why is its degree 3?
X, right, third, x terms multiplied by x terms squared.
Right, we only have things coming to degree 3. Everything is a degree 3 term. We don't have anything to the 4th power. The highest degree of an individual variable is 2.
You say like if the function's multiple variables, the degree
Is the sum of the degrees of the variables in the expression. And so each variable occurs to at most the second power, but the whole polynomial is degree 3. If you look at what's going on in red, the red was just x2 minus x1, x1 minus x0, x2 minus x0. What's the degree of those 3 factors? When you multiply that out, what degree is it? 3. So what can you tell me about this over here? What's its degree? Has to be degree 0. It's got to be a constant. So all we have to do is put in special values of x1, x2, or sorry, x0, x1, x2, and we can figure out what that constant is. So again, we're trying to milk as much as we can from a simple case that we can still do by hand. Okay? Again, this is the 21st century. We have tools like Mathematica available. It's not that bad to use. To do the 1-by-1 case wasn't bad. To do the 2-by-2 case, we got x1 minus x0. And if you look at that, that might suggest that the answer is going to be involving differences of the x's. When we look at the 3-by-3 case, this is where it helps to have access to good programs that can do algebra. The fact that you can plug this into a computer and ask it to simplify, and it will factor this. Now, it factored it differently than I wanted, because it factored it in such a way that there was a negative sign. I'd prefer not to have the negative sign, and I'd prefer to factor it with a large index over the smaller. Okay, but not bad. Mathematica was able to do that. I think it might even be able to do the next one. You should definitely try and see if you can do that. But looking at this, once you factor, does this suggest what might happen if you go up higher? We've got x0 minus x1 minus x0, then we've got x2 minus x1, x2 minus x0, x1 minus x0. Do you think you could predict what comes for the 4-by-4 case? I'm sorry? Not sum. The product. So the product of the pairwise differences. That's a really good conjecture. And the hope is that we now have enough data that that's a reasonable conjecture. So the conjecture is if I give you 1 dot 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 1 x0 to the n minus 1 x1 xn minus 1 x1 to the n minus 1 xn minus 1 to the n minus 1, that this is some constant times the product 0 less than or equal to I strictly less than j less than or equal to n minus 1 of xj minus xi. Do you want to be bold and conjecture what the constant is? We've got some data. What's the constant when n equals 2? One. What's the constant when n equals 3? So do you want to be bold and make a conjecture? Let's conjecture that it's 1. So this is actually a theorem, the determinant of this matrix. So let's talk about how we can prove this just by looking at this. So the first thing is the determinant is a polynomial in x0 through xn minus 1. Does everyone agree that when you expand this out, it's going to be a polynomial? Now, let's talk about how do you calculate determinants. So this is a chance to review some of your linear algebra. So do you remember you basically look at all the different permutations and you take one element from each row and one element from each column, and you look at all the different ways to do it? So if I take something from the first column, what is the power of that? What's the degree of something from the first column? 0. What's the degree of something from the first? 1, and so on and so on. So have one element from each column when expand. Column D gives a degree D term. D goes from 0 to n-1. So I'm technically calling it, 0th column, first column, all the way to n-1. So have something like, x, let's call it, m1 to the d1, x to the m2, d2, dot, 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 x to the m, n-1, dm, n-1, because I don't know which term it is. And so the degrees are 0, 1, 2, dot, 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 n-1 in some order. So does everyone agree that all the terms are going to look something like this? I don't know which index it is, but these are just going to be the numbers permuted somehow, and the degrees are going to be 0, 1, 2, all the way up to n-1. Does everyone agree on that? If not, please speak up. This is the key step here. Okay. So what is 0 plus 1 plus 2? What does this equal? So this is an extremely famous sum.
n-1 times n/2.
It's n-1 times n/2. And one way you can see this is if you write the numbers backwards. Then you get the same thing. And so if you add, you'd get twice the sum. And then each one of these would be n-1, and you would have them n times. So Sn-1 is n-1 times n/2. So the determinant is of degree n-1 times n/2. Okay. I do not want to copy. So let's consider the product 0 less than equal to I less than j less than equal to n-1 of xj minus xi. Do we agree that this is a polynomial? Right? When we expand it out, it's going to be a polynomial. What's its degree? How would you find the degree? So I need to know how many terms are there in the product. So I and j are chosen such that I is less than j, and they go from 0 to n-1. So there's a couple of ways you could try to figure out what this is. We could say, well, look, I could have I goes from 0 to, what's the largest I could be? n-2. And then j would go from I plus 1 to n-1. And I could evaluate that sum. So that's one way to figure out what the degree is. And I'll let you do that calculation. But there's a better way of doing this. I'm choosing two elements from n numbers that are distinct. And then I'm just declaring the smaller one to be I and the larger one to be j. How many ways can you choose two numbers from n? Yeah, better. we have n choose 2 choices for a pair, let's call it, alpha beta, then set I equals to the minimum of alpha beta and j equals the maximum of alpha beta. And of course, I'm assuming alpha, not beta, in the set 0 to n minus 1. And n choose 2 is just n times n minus 1 over 2. So the only difference is, do I write n and then n minus 1, or do I write n minus 1 and n? So we know that this is also a polynomial of degree n minus 2. So if we go back to our conjecture, doesn't let me copy, hide. So now we have 1, 1 dot 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 1 x naught x1 x1 to the n minus 1 dot 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 x naught to the n minus 1 dot 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 x n minus, oh, this should be to the 0 to the first power, sorry. Xn minus 1 to the n minus 1. And over here we have the product 0 less than equal to I less than j less than equal to n minus 1 xj minus xi. And so this is a polynomial of degree n minus 1 over 2. This is a polynomial of degree n minus 1 over 2. So there has to be some constant such that they're equal. The other thing is, if you look at the left-hand side, if you look at the determinant, if xi equals xj, then 2 rows are the same. So determinant is 0. So determinant is a multiple of this product, I less than j of xj minus xi. So this is just a quick way of seeing that I should have expected something like that. When I look at my determinant, I know if I ever take an xi equal to xj, I've got 2 rows that are the same. So the determinant has to be 0. So it has to be a multiple. So the only thing we need to do is we need to figure out what is that c. And I just have to choose special values of x's. I just need to do this for one choice of x0, x1, and so on and so on and so on. Okay? So if we can do one choice that works, we're great. And so the idea is take x0 much less than x1, much less than x2, much less than dot dot dot, much less than xn minus 1. And if you do this, when you look at your determinant, so x naught, x1, xn minus 1, dot dot dot, dot dot dot, xn minus 1 to the n minus 1, x naught to the n minus 1. If you do it like this, so that each variable is much, much larger than the previous, when you look at all the terms in the expansion of the determinant, which is the only term that's going to matter? That's not a term in the expansion of the determinant. Xn minus 1 is just one number. I have to do a choice of one element for each column. So clearly, if I want a large contribution, I want to have the xn to the n minus 1. And you would just see that this is going to be the term that contributes the most. Because this is going to have the highest power of xn minus 1. And then once I have the highest power of xn minus 1, the best I could do would be then have the highest power of xn minus 2. So it's going to look like xn minus 1 to the n minus 1, xn minus 2 to the n minus 2, dot, 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 x1 times 1, plus blah, right? And so this is the main term. What's the coefficient here? Coefficient is 1. And if you look at what we have over here for the product, when you expand it out, because I've got the large index first, when I expand it out, it's going to start off with something like that. And so the C has to equal 1. All right, so this is a good place to stop. But again, the point of today was to talk about how to gather data, how to use that to inform you in terms of making decisions. When you're writing things up, this is a great thing to keep in mind, is putting in some simple cases to have the reader try to build some intuition, but be careful because sometimes the intuition can be wrong.